Good morning, everybody. Should we get started? Should we wait another minute, or I think everybody's here pretty much? Okay, well, I hope you are all doing well this morning. Thank you for coming. So the past 2 days, we've been basically talking about the brain, and first we looked at more of a cellular level. Yesterday we looked at the brain on an anatomical and functional level. And today we're going to start talking about anatomical and functional imaging. So we're going to go over some basic techniques today, and tomorrow we'll start talking about MRI more thoroughly. So just to recap what we talked about the other day, there were early methods of brain exploration that people used, and some of these are still used today, such as animal models, post-mortem dissection, looking at opportunities of diseases and malformations, accidents, and strokes. But these techniques have some limitations and can be sometimes difficult to translate to human subject research. So this is a slide I showed the other day. Right around the 1900s and the turn of the century, some new techniques started coming about. EEG was an early technique to measure electrical activity from the brain. X-rays and radiography came around almost around the turn of the century of the 1895. X-rays are wonderful for seeing a lot of anatomical tissue in the body. Unfortunately, soft tissue is not one of the strengths of X-rays, so it's still difficult to see the brain tissue with X-rays. And of course, CAT scans are sort of a 3D reconstruction of X-rays. We're going to talk about both of those a little bit today. MEG came around in the late 1960s, and this is very similar to EEG, but it looks at the magnetic fields that come from the brain rather than the electric. Then MRI came about around the 1970s. This gave us a better ability to see soft tissue. And right around the same time came PET scanning, which is positron emission tomography. This was used and is used still today to measure metabolic functions. Functional MRI came about in the 1990s, and around the same time came diffusion tensor and white matter tract imaging. And we're going to talk about each of these a little bit. Now, this is not an exhaustive list, so there are other techniques that people use. And there is NIRS, which is near infrared. We're not going to talk too much about that, but that's a newer technique that people use as well. So I know we talked a little bit about the distinction between structural and functional imaging. Just to recap on that, structural imaging is designed to see anatomical features of the tissues. So X-rays, CAT scans, MRIs, even diffusion tensor imaging is a structural anatomical method. And these methods are great for clinical assessments. So to look for tumors, to look for damage to the tissues. In research, these techniques are used to look at structural integrity of the tissues, so seeing how well the tissues are intact. Tissue volume studies are often used, like trying to compare different sizes of structures in the brain from different subject groups. Functional imaging, on the other hand, is designed to see functional processes, so things that are actually actively happening in the brain. Functional MRI, PET scans, EEG, MEG, and I mentioned that NIRS, near-infrared spectroscopy. These are all functional methods. So we're not actually looking at structure, we're looking at the workings of what's happening in the tissue. These are used for clinical assessments to a lesser extent than structural. So these are really new methods, a lot of them. The ones that have been around longer, such as EEG, are often used for clinical diagnoses of epilepsy, and we'll talk a little bit more about that. But functional methods are more widely used in research than the structural techniques are. So before we start talking about these, I just want to talk about taking pictures. So, you know, when you take a picture of something with a camera, you basically need the camera and you need light, right? So these are to take an optical picture, and this is what people typically think of when they think about taking a picture. So the question that I pose is, how do you take a picture in the absence of light? So these methods that we talk about today and over the next few days are about taking pictures, but they're about taking a different kind of picture, not a light picture, which is really cool. So a lot of these techniques that were developed, I think, are very clever, and whoever came up with these, I think, are just really on top of their game. I wish I could develop something as cool. So as we go through these, we're going to be asking that question, what are we actually using to take the picture in these techniques? So we're going to start up with structural methods. We're going to talk about X-rays, CAT scans, just briefly today about MRI and DTI, because we'll dive into those subjects much more deeply in the next couple days. So X-rays came about in the late 1800s, right around the turn of the century. They were developed by, I'm not sure how to say his name, Wilhelm Conrad Roentgen. Does that sound right? Roentgen? Okay, I believe you guys. He was a professor at Würzburg, is that right? University in Germany. He was working with a cathode ray tube in his laboratory, and in doing so, he accidentally discovered X-rays. So he was working with these, and he noticed that the X-rays were leaving impressions on a piece of film that he had, and he noticed that you could start taking a picture with these. So it was a surprise discovery on his part. So X-rays are electromagnetic energy waves that act similarly to light rays, but at much smaller wavelengths. The wavelengths are so small that they can penetrate human flesh, but not higher density substances such as bone or lead. And then using this idea, you can generate a photograph with them. So X-rays work best for bone or hard tissue. So here's the electromagnetic spectrum, and visible light in this picture is right in the middle, and the X-ray is to the right of this. So you can see it's a much smaller wavelength, and in fact the wavelength is so small that it can travel between the spaces in your tissue and come out the other side. And this is the advantage of using these X-ray to image body tissues, because it passes through some tissue and it doesn't pass through as well other types of tissues. So X-rays are electromagnetic radiation composed of small packets of energy called photons. They travel at the speed of light and in straight lines, and they're highly penetrating. They're also invisible, and if you put a radiographic film behind them on the other side, it blackens the radiographic film, and X-rays also produce scatter. So here's an example. You put your hand up and you have the X-ray go through. Some of the X-rays are absorbed, some pass through the tissue, and some are scattered. But because they're passing through the tissue at different amounts based on the properties of the tissue, you can generate an image on the other side when you pass it through. So it's passing through the skin and the soft tissue more than it is through the bones. So as the distance from an object is increased, the strength of the X-ray beam is reduced. So less X-ray will reach the film. So low-density tissue allows more X-rays through, thus causing the film to turn black on the other side. High-density tissue allows less X-rays through. And as X-rays hit the atoms in the film, it causes it to leave an image. So X-rays, as you know, are great for imaging bones, looking for breaks in bones. And but they're very difficult to image soft tissue with these because they seem to pass through soft tissue pretty much equally, and so it doesn't make a good contrast in the soft tissue. Another limitation of X-rays is that they're fairly low resolution, and they're also two-dimensional. A negative side effect of X-rays is that they use harmful ionizing radiation. So ionizing radiation means that it can free electrons of the atoms as it passes by. So these gamma rays are coming through, and they are knocking the electrons off atoms as they go through, and this can damage the tissue and lead to tissue mutations. So as you know, if you don't want to be exposed to too much radiation. It can often, they say too much of it can lead to cancer. But a good thing about X-rays is that they're very fast and they're very inexpensive. So if you go in with a complaint that you maybe broke a bone or something, they'll immediately do an X-ray. But you want to be careful not to get too many X-rays in a year. I know you get a lot of radiation from other sources as well. So it's really hard to say how much is too much, I suppose. But somebody else thinks a lot about those things and can give you the numbers. So CATscans came about but using this X-ray technique, and CATscan stands for computerized axial tomography. It was invented by Sir Godfrey Newbold Housenfield. And tomography, the word tomography is basically using X-rays in projective geometry to represent a single slice of the body on radiographic film. So this came about in the of course, X-rays came about in the early 1900s. CAT scans came around, the first commercial scanner was in 1967. So CAT scans are basically using an X-ray to make a 3D image. So it's employing digital geometry to take these 2D images that X-rays make and produce a 3D image from it. The first brain scan of using a CAT scan was in 1971, and it used 160 parallel readings through 180 angles. So I'm going to give you an overview of how you would reconstruct an image using a CAT scan. But they're done using algebraic reconstruction on a large computer. And of course, now a large computer is not as much as a worry as it was back in the 70s. So how are these CAT scan images formed? Well, again, they use the X-ray methodology, but it's a multi-step process to create the image. So you see the person lying there, and the X-ray source is basically circular around the body, and the X-ray beam passes through edges of a slice of a body tissue, and the beam is rotated around the body. So as it's rotating, it's taking multiple images, and the X-rays penetrating to different angles depending on the tissue that they pass through. And by turning this and taking multiple images, you can use this to form a three-dimensional image around the body, or of the body as it goes around. So you see here, this is just a schematic. At the top left, the X-ray scanner is passing through, and you remember the X-rays are going to scatter and create this image on the other side. So as it does this, collects the data and then does an image reconstruction. And you see here, this is a little bit older because it says taking the digital image and making an analog conversion. Of course, now we use a lot of digital imaging, but these are the basic steps. So collect the images and reconstruct the image, and then have your output image. So again, slices of the tissue are formatted around a person. So instead of collecting a two-dimensional picture, you're getting a three-dimensional picture. So this is where we go from pixels to voxels. So have you all heard of pixels? Just basically a small picture element. So when we talk about a lot of our brain imaging techniques, we're going to be talking about voxels. So instead of a picture element, it's a volume element. So you're thinking of a three-dimensional little piece of tissue rather than a two-dimensional square of tissue. So each voxel contains a volume of tissue represented by uniform intensity. And this is important because the size of the voxel that you get is going to impact your image resolution. So if the smaller, it's just like a pixel. So the smaller the pixels are, the better resolution you get in the image. And this is the same of a voxel. The smaller the voxel you have, the better the image resolution you can get. The intensity of the voxel in the case of the CATscan is related to the density of the tissue. So what are we imaging here? We're imaging the recorded amount of the X-rays that are coming through onto a piece of film after it passes through the tissue. In CATscan imaging, water is used as a reference and is assigned a value of 0. So tissues that are more dense than water will have a positive number. Tissues that are less dense than water will have a negative number. And this is the basic formula of it. So you take your measure of your tissue and you normalize it to the density of water, so that water will have a CT number of 0. So high density areas appear white, low density areas appear black. And then to reconstruct this image, they use back propagation. So what is back propagation? Okay, so this is just a little schematic, the next couple slides, of how back propagation is used. So the scan view through a section containing the object. The data produced is not a complete image, but a profile of the X-ray attenuation by the objects. So in one dimension, if we try to image this image on the left, and you just take the first dimension, you'll get something like the image on the right. Right? You'll get darker areas and lighter areas depending on the shape of the object. So you collect this at many different angles. So here, this would be in 2 dimensions. So if you only took one view and then you turned it orthogonally 90 degrees and took the next view and used this back propagation technique, you would get an image of the kind on the right. So does everybody see that? How we're taking the one image and we're combining it with the second image so that the areas that are less dense and more dense have different intensity values on the image. So you do this again, rotate it again, and rotate it again till several hundred views are used, and in doing so, you can start to form an image. So keep projecting planes and keep turning it, and eventually you will end up, by combining all these with an algebraic technique, you will end up with your image of the object. So it's more complex than that, but I'm just trying to give you a conceptual view of how this is done. And they also can use a high-pass filter to remove low-frequency blurring. And this back propagation technique is also called a summation method. So does that make sense to everybody, how that's the basic concept of how that's done? So after doing this in 2D and in 3D, you can end up with basically a three-dimensional picture. And this is a two-dimensional slice of a three-dimensional picture of the brain using CATscan. So because CT scans are three-dimensional, the brain tissue can be imaged. It can reveal gross features of the brain, but it doesn't resolve the structure very well. So you can see here that there's not good differentiation of the different tissue types in the brain, but you do get a pretty nice picture of the overall image of what it looks like, and you can see differences pretty clearly in the skull and in the fluid spaces of the brain. But in the tissue of the brain, it's not very good resolution. So CAT scans are good for the evaluation of cortical bone and metal or foreign objects, but again, not so great for brain tissue. on a scale of, finer dimensions. So we haven't talked about MRI yet, but we're going to talk about MRI. And just right now, I just wanted to show you what a CAT scan versus an MRI looks like. So on the left with the CAT scan, you get a white picture of the bone. On the MRI on the right, you see much more of the detail of the soft tissue than you do of the bone. And so just briefly, this is a very early MRI picture on the right. Felix Bloch and Edward Purcell independently discovered magnetic resonance phenomena in 1946. They were both awarded a Nobel Prize for this in 1952. And the magnetic resonance that they used was mostly for nuclear magnetic resonance, NMR at the time. But later in the century, Peter Mansfield and Paul Lauenberg then used MRI to start creating images. So this was a very clever way to take an NMR data and turn it into 2 and 3 dimensions. And like I said, we'll talk about that in a lot more detail tomorrow. But the first MRI machine was in 1972. MRIs use strong magnetic fields and pulses of radio waves to generate pictures of structures and organs. And MRIs, the great thing about MRIs is that they don't need nuclear medicine or contrast agents. So you don't put any ionizing radiation in, and so the person isn't exposed to any harmful rays. And you don't have to use a contrast methods to get a very nice image. They're sometimes used in special cases of trying to look at special things, and we'll talk about that with MRI. But MRIs are wonderful for imaging soft tissue, and me, myself, I'm sort of partial to them because I work in that area. So MRI machines can go up to as much as 7 Tesla today, which you're going to see when we talk about MRI tomorrow, how impressive that is. But using a 7T image, you can get very fine detail of the tissue. So bringing this up, the point I wanted to make here is, why would anyone ever choose a CAT scan over an MRI then? If you go and are having a problem, they might do a CAT scan of your head. And I can remember a case where my son was having a problem with his head, and they brought him in immediately and did a CAT scan. So you might think, why wouldn't they just do an MRI on him? They have a lot better resolution. They can see a lot more. So the answer to that is that CAT scans are less expensive and they're much faster. So in cases of trauma and emergency, they're often chosen over an MRI. CAT scans are also better for certain patient types because they're a lot less sensitive to motion. They're faster to collect, so the patient doesn't have to lay still as long. Another issue with MRI machines is that they can be very enclosing. So to keep the magnetic field nice and even, you need to have a round circular space for the field to be generated, and the person goes inside that. So the smaller that space is, the better field, the evenness of the magnetic field you can get. So people who are claustrophobic or people who are heavy sometimes will feel uncomfortable or may not even fit in the MRI machine. So CAT scans are better from this aspect. So MRIs also, since they use this big magnetic field, can be limiting for people with implanted medical devices or with metal in their bodies. So if you have a pacemaker or anything that runs on electromagnetics in your body, you don't want to expose this person to an MRI. Also, however, CAT scans use ionizing radiation, whereas MRIs do not. So again, ionizing radiation means that the radiation carries enough energy to knock electrons off of atoms in the body, and this can be harmful to a person if you expose them to this repeatedly over and over again. So that's definitely a downside of CAT scanning. But again, as far as trauma and in expense, CAT scans are often chosen over MRIs, and for this reason. So while we're on the subject of anatomical imaging, we're going to talk briefly about diffusion tensor imaging. And we're going to have an hour lecture devoted to this later. This is a really cool technique, I think, and it's one of the more recent techniques that people are using and are really focusing on to image basically white matter tracks in the brain. And diffusion tensor imaging uses principles of magnetic resonance imaging, but it's based on the theory that water traveling through axons in neurons is limited to flowing in a certain direction. So the picture on the left shows isotropic diffusion, where the water molecules can move randomly anywhere they want to go. And the picture on the right shows anisotropic diffusion. So the water molecules are constrained by the shape of this tissue, which is, in this case, are the axons that are run parallel to each other and only run mainly in a single direction. So we take advantage of this property to image white matter tracks, and people call this sort of imaging connectivity in the brain. So whereas before that white matter just sort of looked like a blob of white in the brain, now we can start to make distinctions in the tracks that run from the gray matter areas to connect areas in the brain, which is very important when we're starting to try to understand the functional integration of different areas in the brain and how they work together. Okay, so now we're going to move on to functional methods. And today we're mostly going to talk about EEG and PET. We're going to talk about fMRI just briefly today, and we're going to have a whole 2 lectures devoted to that later on this week. EEG you might not think of as an imaging technique, but by definition, it's used to study functionality in the brain and try to specify it to certain locations. So it is considered a neuroimaging technique. So when we talk about functional methods, we want to make the distinction between direct measures of brain activity versus indirect measures of brain activity. So direct measures are actual measures of the neuronal activity, or we think that they're direct measures of the neuronal activity. So in this case, an EEG, which is an electrical recording of the brain, we think is a direct measure of what's happening in the underlying tissues. The neurons are firing, and we're placing electrodes on the scalp, and we're measuring this activity. MEG also, which is the magnetic version of EEG, is also thought to be measuring these direct activities that are going on in the brain. And we measure these, of course, from the scalp. And in some cases, EEG is measured directly on top of the brain when they're looking especially at clinical cases of epilepsy. When we're going to distinguish those direct measures from indirect measures. Indirect measures are a side effect of the neural activity. So positron emission tomography, which is a measure of underlying metabolic activity, is not a direct measure of the brain activity. So the brain is being used, and in using the brain, we're doing things like using glucose and other types of things, and this is what we're actually measuring. So if we use PET to measure, as we'll talk about later, glucose metabolism, we're looking at the energy usage that these neurons are going through as they're working. So we can see which areas of the brain are using the most energy. Similarly, fMRI is a measure of blood flow changes in the head. So we're not looking at direct firing of the neurons, but we're looking at changes in the needs of the neurons as they're being used. And the body, as we mentioned yesterday, places a lot of importance on the brain and making sure that the brain gets the blood flow that it needs. And so when we use different regions of the brain, the blood flow needs in those regions locally changes. And that's what we measure. Okay, so EEG. We're going to talk more about this now. We're going to talk about what it is and the brief history of it. We're going to talk a little bit about how it works and its basic principles. We're going to talk about collecting the data. We're going to talk about some of the problems that we face when we deal with EEGs. And we're going to talk about applications of EEGs, which is going to include evoked potentials. Probably some of you who work with the brain have heard of evoked potentials before, but we're just going to talk briefly about those. Sir Hans Berger first recorded an EEG signal in 1924. And as I said, EEG measures direct electrical activity from the brain. And the activity that it collects is known as brain waves. So you can see underneath the 1924 Sir Hans Berger, those are, well, at least the top one is a brain wave that's collected using EEG. When you collect data using EEG, you're measuring summaries of inputs to a group of neurons. So you're not measuring each neuron singly as it fires, but what you're getting is basically a summation of what's going on underneath the part of the tissue that you're looking at. EEGs are used clinically to assess abnormal electrical activity in the brain, especially in the cases of seizures. But they're used a great deal more in studying brain function. They're used quite a bit in sleep research, and as I mentioned before, people use evoked potentials. I think evoked potentials are also used clinically to see if there's a disruption in the flow of information through nerves. Okay, so let's talk about the basic principles of EEG. As neurons fire, so fire means these action potentials that they're getting. So a signal comes along, the neuron does its action potential and passes it along in the electrical activity propagation. As they do this, electrical activity is generated. And with EEG, we can measure the spatial distribution of this electrical activity. So we're looking at the voltage fields created by the brain, and we're looking at the variation in these over time. As I mentioned, the activity that's measured on the surface of the brain is a summary of all the local electrical activity that's going on underneath the scalp, underneath the meninges, and underneath that cerebral spinal fluid. So the signal that we get is summated from what's going on locally, and it's also highly filtered. Filtering means that it has to pass through all this other tissue. So we're getting, what we're seeing is, it's not like a distorted thing, but we're seeing a summation and a filtered signal. The activity that we record is thought to be mostly from the cortex, and we're going to take a look at what some of these waves look like. Like I mentioned, EEG is often used to study sleep, so that the EEG waves that you measure during sleep have been widely characterized, and these are often more slow and more rhythmic than what we see if a person is awake. So these sleep waves that we record are thought to be from deeper areas of the brain rather than on the cortex, but they're so prominent within throughout the brain as we sleep that you can measure this slow wave activity on the surface. EEG gives excellent temporal resolution, so we're recording what's happening as it's happening. It's very fast. The problem with it, though, is that it's hard to localize where that activity is coming from directly, because as I mentioned, it's a summation of what's going on in the tissue. It's also being filtered through a bunch of other types of tissues that are not generating these waves. So it's really hard to pinpoint where the activity is coming from. And people have been looking at problems of trying to find a source or a generation of where these waves are coming from. So they try to look for the generator of these sources of activity. And it's a very difficult problem. We'll address it just briefly later. Okay, so as I mentioned, the EEG is a summation and impeded by layers of tissue. So we get this poor spatial resolution. And you can see on the surface there are EEG electrode and what the signal is passing through to get to that electrode. So the EEG signal itself reflects a voltage difference from one electrode to a reference point. So to measure a voltage, we have to have the electrode and we have to have a reference electrode. So we're looking at the voltage difference between 2 points in the brain. And the way that we set these electrodes up on top of the scalp is called a montage. So that montage is basically how you are setting up the electrodes. And there's different ways that people do this. So you could do a sequential or a bipolar montage. So if you do this, each channel represents difference between two adjacent electrodes. So you might put your measure electrode and your reference here, and another one here with another reference, another one here with another reference. So you're referencing the voltage between two distinct channels for each electrode. You can also do a referential montage where you have just a designated electrode that's your reference, and each channel represents a difference between that electrode and this one single reference electrode. So that's called referential. Average reference montage. So you're looking at the average of all the amplifiers are averaged and summed. That doesn't make any sense. So all the channels are averaged and summed, and this average could be used as the common reference. And there's another one that I found called Laplacian montage, where each channel represents the difference between an electrode and a weighted average of the surrounding electrodes. So I would say that the first two are the two most common montages used. One having each channel has a reference electrode, or there is a single electrode placed on the scalp that's a reference to all the other electrodes. So to collect the signal, the scalp electrodes are essentially glued to the head with a conductive gel. So to do this, you take a little small scrub brush and you scrub the area that you're about to place the electrode on with an abrasive. That's to try to get rid of some of the dead tissue and to try to get a better signal from the scalp. The electrodes are then hooked to a computer for the signal recording. And again, this montage that we use can include anywhere from 4 to 128 or more electrodes. So people are trying to measure more and more electrodes as we go on. And with a high number of electrodes, we call that high density EEG. So the idea of that is you're trying to get as best a spatial resolution as you can from these electrical voltages that you're measuring. So to apply the electrodes, in the cases of these high density EEGs, we often use a net or a cap. And you can see the picture on the right where they're using a net to apply this to this girl, because that takes away a lot of the measuring that you need to do, which we're going to talk about when you do EEGs. So you just place the cap over the head, and then in this point you would scrub a little bit underneath the electrode, and then you would, in this case, you could see there's holes in these, and you would insert the gel with a needle into these little holes. And that gel is important to be conductive between the skin and the electrode itself. Typically, a standard international 10-20 system is used to describe the location of the electrodes on the scalp. So this was done as a standardized way to be able to compare and reproduce data across different labs, across countries, and across the world. So if you use this technique, you use the standard um, what do you call, I'm sorry, I'm lacking the word here. You use the standard reference letters. So you use P for frontopolar, F for frontal, C for central, P for parietal, O for occipital, and T for temporal. And we talked a little bit about each of these lobes yesterday. So we have the frontal, the parietal, the occipital, and the temporal. And using this 10-20 system, the odd numbers represent electrodes on the left side of the head, and the evens represent electrodes on the right side. And these A channels represent ears. Okay, so how would you place these electrodes on the head? And we actually have a study right now where we have a bunch of techs that come and do this. And this can take on the order of, depending on how many electrodes you're placing, this can take from minutes to hours. So sometimes it gets very hard for the patients to sit that long. We look at a lot of PTSD people, and a concern that we have is when someone's placing these electrodes on their head, they're very kind of close, up close and in your face. So some of these people with PTSD who get nervous by having people so close and crowded into them are sometimes more difficult to place electrodes on. You need to be considerate of how they feel, and you don't want to get them overwhelmed or freaked out, so to say. So to start placing the electrodes, you would measure from the center line of the scalp, from the nasium, which is called the bridge, which is the bridge of the nose, is the nasium, to the inion. The inion, if you all feel the back of your head, you can kind of feel where the scalp ends and drops into soft tissue, sort of right here at the nape of the back of the head. That is called your inion. So you measure first from the nasium to the inium, and then you take 50% of that distance, and that is the first electrode that you mark. That is CZ, as you can see right there in the middle. That's the vertex of the head. So after you measure CZ, then you mark and you measure and mark 10% up from the nasium, 10% up from the inion. And you continue, then you measure and mark 20%, and you continue to do these 10 and 20% measurements. This is why it's called the 10-20 International Placement System. So you can sort of see how they're getting an even distribution over the head here. So after you measure in this direction, then you measure the pre-auricular point, which is the indentation. Here you can see on the left ear, right next to your ear, and you measure that from ear to ear, and then you mark 50% of the total of that point. So once you do that, then you can see where it crosses the point you measured from your nasium to your inium, and then you mark your true CZ. So the first one you marked was just to keep it sort of a placeholder, but once you see where that crosses the two lines, that's your true CZ. So then you would measure and mark 10% of that, and you would continue in this way doing the 10-20 system. And after you're finished with your marks this way, then you start measuring around the head like this, the circumference, and you basically work your way across the whole head until you have these electrodes placed in this even and standard pattern. And so everyone has the same F's and C's when you look at another person's data and want to try to compare your data to theirs. So in the case of a few electrodes, you might end up with what you see there on the left. If you want to do higher density, then you might end up with what you see there on the right. So you continue with placement until the desired number of divisions is made. So you can see where this would take a long time and the benefits of using a cap or a net at this point. So you get the person all wired up and you plug them into the amplifier, and then you start recording the signal. So this is what a normal awake EEG signal might look like. And for reference, what you're measuring on the scalp is in the order of about 100 microvolts. So it's not like you're getting these big blaring electrical signals, but you're measuring the activity that's there under the scalp. So again, it's about 100 microvolts on the scalp, and if you do measurements directly on the brain, like I mentioned that they often do in epilepsy patients, you might get 1 to 2 millivolts on the brain. And they do this actually by opening the scalp and having a person surgically place these on their head and then monitor them. And you think, wow, that's really an intense procedure. Why would they ever want to do that? Well, that's done in the cases of especially children who have severe epilepsy and have trouble functioning from day to day because they're having so many seizures. So what they want to do in this case is localize where the cells are that are firing. Epilepsy is due to the misfiring or just sort of wild firing of cells in the brain. So they're trying to find these cells that are behaving badly, and they want to cut these cells out or try to isolate them from the rest of the brain by cutting off their neurons. So that's a case where they may open up the head and use EEG actually directly on the brain. So after you measure the signal, you want to try to reduce artifact before you actually start analyzing the signals. And artifact reduction can be done using filtering to get rid of potential signal drifts or high frequency artifact. Then we can do the analyses. So time frequency analysis is commonly carried out using EEG analysis. And we'll talk just a little bit about time frequency analysis. For those of you who've done signal processing, you may be familiar with time frequency analysis. Another thing that's done is features of the EEG are often tried to be looked at and extracted to characterize the signal that's coming. So I mentioned you want to try to get rid of artifacts in the EEG signal. These artifacts are noise and things that you don't want to see in there because they're not attributable to what's happening in the brain. Sometimes you'll see cardiac artifacts from the heartbeat. You might see electrode artifacts. This might happen if a person is sweating or the electrode becomes loose. And we see this happen often if you have electrodes placed on somebody's head and have them sleep with them on. Oftentimes they'll start coming loose in the night. So you may see external device artifacts. So noise from nearby electrical activity could be picked up by these electrodes and can be reflected in this actual signal that you're measuring from the head. Other types of artifact include muscle artifact. So when you use your muscles, you're also generating a little bit of electrical activity, and this could be present in the EEG signal, especially if somebody is sleeping and they're grinding their teeth. So you'll see electrical activity from these jaw muscles working. Ocular artifacts are artifacts from the eyes moving, and we also see this in sleep because when a person is in REM sleep, it's rapid eye movement sleep. So you might see these eye artifacts, especially when you're looking at the electrodes up here in the frontal lobe. We're going to look at each of these artifacts a little bit. So you can see this is an electrode recording, and you can see, I don't know if you can make out the detail on the left, but this looks like a bipolar placement. So they're referencing, in each case, between two different electrodes. And you can see the one in the box there. You see how it has this rhythmic spike every so often? Now that is due to the cardiac signal. And if you can identify this as being a cardiac signal, then you can design ways to get rid of that before you analyze your data. So you don't actually analyze the cardiac data as part of what's going on in the brain. Okay, so this in the little circle there is called an electrode pop, and that pop, it's caused by the electrode coming loose. So you get this high spiking activity from the electrode. Okay, so this is a pacemaker artifact that's being shown in the EEG, and it's really hard to tell. I wonder how, to myself, how they actually picked that out of this signal, because it doesn't look that different from the rest of the signal. But whoever did this obviously knew what they were doing and can pick that artifact out of the signal there. And again, once you know what kind of artifact you have in your signal, then you can deal with ways to remove it without actually destroying the whole EEG signal. So here's some muscle artifact. You can see this very high frequency activity up in the and sort of in the center of on the top electrodes. So it's high amplitude, very fast activity, and it's due to facial muscle contraction. Okay, so eye flutter artifact is something else you might see. And they have that in the box at the top. You can see that's a very rhythmic artifact activity. And if you look at this again, in this middle channel here, you can see that cardiac artifact again. If any of you know what an EKG looks like, it's sort of showing up here in this. Do you see where I'm talking about here? So how do you get rid of these artifacts? Well, one way to do it is, and they actually have people who do this, just scroll through this data over time and try to visually identify these bad epochs of data and just manually remove them. So we have people who, it's called scoring sleep. So we have this overnight sleep activity of hours, maybe 8 hours of data, and they go through that by hand and score the sleep into stages. So we'll talk about sleep a little bit more today, and we'll talk about it in detail, but you can recognize based on the EEG signal, based on this slow wave activity and different features that you see in the EEG, what stage of sleep somebody is in. And so as they're doing this, they can pick up where they see these noisy regions of activity and just select them and remove them. Of course, then you're getting rid of some of your signal, so you're not quite, sure what's going on during that time period. So that's not really an ideal way to do it. Another way you can do it is by signal subtraction. So on the bottom left here and on the bottom right, you see the EKG signal. And this is a very common type of signal that's easy to characterize. So on the left, the EEG signal is before they removed this EKG signal. And on the right, what they did was they took this EKG signal and subtracted it out of the EEG signal. And you see on the right there, they get a much cleaner looking signal. Okay, the ocular movement during REM sleep again is a type of artifact that you can see in sleep EEG. And the cool thing about that is the way that you place the two eye electrodes, you can do it to make the ocular activity equal in opposite directions. So as you can see in this little box, as the one eye goes up, the other eye goes down. And a little bit later on, again, you see that. And you can actually define what these artifacts look like to a program. So look at an area where the signal's going exactly 180 degrees apart at the same time in the eyes. And you can use this strategy as a way to remove the signal. So you would determine where the signal changes exactly opposite of the other and remove this from your EKG signal. So I think maybe we should take a break now, and then we'll get into more of the applications of the EEG after the break. My lecture today just goes on and on, so it's not two distinct lectures, it's together. So we'll do that. Sound good? Okay. All right, so back to EEGs. And we talked a little bit about what they are, how to collect them. So we're going to look a little bit at what EEGs look like. So this is a type of normal adult brain waves that you might see. And the top one is a person that's awake, thinking about something. These are called beta waves. They're in the range of 14 to 30 hertz. Do you guys have signal processing background at all? Frequencies? Okay. Yes? Did I ask if you have signal processing? Yeah. You do? Okay. It helps if you have some signal processing, but hertz is basically a measure of the frequency, so how frequently something is occurring. So when you see these waves, for example, the bottom one has a lower frequency. As you can see, the waves are slower, and the top one has the highest frequency in this plot. So when you're awake, you have a higher frequency activity in the brain, and when you're awake and resting, I think it's with your eyes closed, is the alpha waves. And as I mentioned, as you sleep, you can characterize what stage you're in by what types of brain waves that you see. And the deeper sleep that you get into, the slower the waves. So when you're asleep in one of the earlier stages of sleep, for example, stage 2, you might get theta waves there. And when you go into a very deep sleep, you get this slow wave, repetitive activity through your brain. And sleep again, you can see the waves there. Stage 1, you can see the theta waves. And they sort of oscillate with these alpha waves. So as you're falling asleep, you start to see these sleep waves in the brain. And as you go into stage 2, which is a little bit of a deeper sleep, you start seeing what's called sleep spindles. And there's one shown in the box there on the left. And you see these things called K complexes, which have a very characteristic type of wave. And then as you get deeper into sleep, into stages 3 and 4, you see these slower delta waves, which were the slow waves we saw before. And then you actually go back into REM sleep, which looks a lot like awake EEG, with a little, like maybe stage 1, not completely awake, but you cycle through these stages throughout the night. Okay, so in research, EEG is used in different ways. People look at evoked potentials. They look at time frequency analysis. There's been some work with people trying to regulate their own EEG signals. We're going to look at that. And as I mentioned before, source localization, which focuses on trying to find where the source of the EEG activity is coming from. Yes? Yes. Because of the pattern, that's a great question. So you see this throughout the brain when you measure sleep waves. So this is how people characterize, but I think they're more prominent in certain locations than others, but you can pretty much see them occurring throughout the whole brain. Sure, that's a good question. Okay, we're going to talk about evoked potentials. Oops, I'm missing a parenthesis on the right side. Okay, so an evoked potential is an electrical potential measured from a human or an animal following the presentation of a stimulus. So the stimulus can be sensory, visual, auditory, or somatosensory, a touch, motor, or related to an event. So what happens for these ERPs is that you elicit the stimulation and then you measure the response. So some types of evoked potential waves have been well characterized. We're just going to look at one such type here, which is a visual evoked potential, or a VEP. So this is an evoked potential that's measured while you're looking at an alternating checkerboard. So remember, we said the visual system of the brain focuses a lot on the lines and patterns. So when you have somebody looking at an alternating checkerboard, this gives a big response in the visual cortex of the brain. So you generally only need to use a single electrode over the occipital cortex and a reference electrode. So in the picture there, it looks like they have the OZ as their measurement and the FPZ as their reference. And interestingly, if you do this in many different people, you see pretty much the same waveform if they're all healthy. This is what the visual evoked potential looks like after looking at that alternating checkerboard. So you can see here the voltage, and you see on the left the stimulus onset. Then you have a latency. The latency is in terms of milliseconds, so this happens very quickly. So initially you get a negative peak, and then it's followed by a positive peak, and so you can see here N75 and P100. These numbers that they use, 75 and 100, indicate the average peak latency from the stimulus. So you're measuring basically how much time has passed between your stimulus and when you're measuring these waves. So you can look at to assess this person's VEP, you might look at the latency of these peaks, see how quickly they correspond to, how well they correspond to the times, and how much peak you generate from this. So when you collect evoked potential signals, they're often noisy. And one thing that you can do to sort of reduce this noise effect is do what's called ensemble averaging. So you collect a signal over and over again, and you expect that you're going to get the same signal each time that you collect it. And you also know you're going to get some noise in there. So you assume that the noise is randomly distributed. So you're assuming that it's white noise, and if you sum all the noise up, it's going to equal to 0 because it's just random. So you keep collecting over and over again, and then you average the signal, and by doing so, you increase the signal strength, and you reduce the noise because you're assuming the noise is going to 0, and your signal is getting more and more prominent as you measure these repeatedly. So you can see on the left what it might look like of several measurements, and on the right, then you get your nice VEP waveform. Another type of analysis that's done with EEGs is time frequency analysis. So time information is important for understanding time and amplitude information, how quickly things are occurring in the brain. And like I said, one benefit of using EEG is that you get very good temporal resolution. There's very little lag time between when the signal occurs and when you're collecting it. So the frequency information can help us understand information about magnitudes and frequencies of the brain. Frequency information doesn't give time, but if you combine it with this time frequency analysis, then you can look at how these frequencies occur over time. So just to repeat that, if you just take a time signal and put it into a frequency domain, you're not looking at what's happening over time. You're looking at how quickly your time signals are changing. But if you combine this time frequency analysis together, then you can see how the frequencies are changing in the brain over time. And to get from this time domain to this frequency domain, you use what's called a Fourier transform. And you can also take something from the frequency domain back to the time domain by doing the inverse Fourier transform. So here's the basic Fourier transform. And I don't want any of you to have to memorize this or feel intimidated by it, but it's a very clever tool that we use to get information from time to frequency and vice versa. And you'll see again when we start doing MRIs that we use a two-dimensional spatial Fourier transform to get the brain images that we measure. So this is sort of a visual description of how you get from a time domain to a frequency domain. So the Fourier transform, again, is a mathematical tool to decompose I should say, time signal into a sum of sine and cosine waves. So if you've had any trigonometry, you might know about sine and cosine waves. So I used to be very intimidated by the Fourier transform. I'd look at it and say, oh my gosh. But actually, when you think about it conceptually, it's not a very hard concept. So if you look at this plot on the right, I don't know if you can see it, but there's a time signal in the red there. And you can take that time signal and you can represent it by sums of sines and cosines. So if you look behind it here, you can take this signal actually and decompose it into, again, to sums of different frequency waves of sines and cosines. So all you're doing basically is taking this function and breaking it down into these different types of frequency waves. And if you take the frequencies of those waves and put them on the axis here that you see in blue, then you can represent this time signal by a frequency estimation of what it looks like. So again, it's just basically breaking your signal down into sums of sines and cosine waves and showing how a picture of what those sums of sines and cosine waves look like on the frequency axis. And you saw that the Fourier transform can be a difficult calculation. So somebody came up with this fast Fourier transform, which can be used to compute a discrete Fourier transform pretty quickly. And you can, let's see. Okay, so uses of a Fourier transform might be in acoustics, in the study of sound. We can break down our sound waves into also these sums of sines and cosines and represent them musically or on a frequency distribution of music. Radio waves, sonar, imaging. If you've ever studied theories of mechanical vibrations, they also break this down into using Fourier transforms. And geology information, such as earthquakes and how the earth shakes, can also be broken down into frequencies. So basically anything that you can collect in a wave, a time wave, you can break down using the Fourier transform. Okay, so we can take an EEG signal and we can also represent this as a frequency signal. So if you look at the left, you see this very steady plot here on the top. That's a lower frequency, meaning it's a slower wave. And because it's just one perfect, you can represent that as one perfect sine wave. You see it's just a spike in the frequency domain. So it's a wave that's going at a very specific frequency. So it's represented as a spike again in the frequency domain at how fast, at the speed that it's going, basically. And as you get faster and faster frequencies, of course, your spike's going to move up on the frequency domain. Does that make sense to everybody? And if you would put these all together and get the signal at the bottom, then you could represent this bottom signal of how much of each of these waves are embedded in this signal. So you can do time frequency analysis, like I said. One thing about the Fourier transform is that it assumes that you're looking at an infinite signal. So when you do time frequency analysis, you have to pick a chunk of signal over time, because remember, we want to look at how our frequencies are changing over time. So we can't take this infinite signal and make it into a Fourier transform. You have to, in this case, pick a window size and do the Fourier transform of the signal within that window. And then you move it along and do another Fourier transform, etc. So you take this block of time and you compute frequencies. And of course, the longer window length that you have, the better resolution of the frequency signal you'll get. But we can look at these and how these signals change over time, and you might get a pattern that looks like this on the right bottom here. So you're looking at how your frequency signals are changing over time. we could take this and then we could attribute this signal at each electrode location in the head. And then we can show where slower waves are present in the head and where faster waves are present in the head. So this is a plot showing where the distribution of frequencies lies in relation to our electrode placement. So areas between the electrodes, we don't have signal there, so you can interpolate between electrodes to get these nice smooth patterns. And of course, the more electrodes that you have, the better resolution of the signal you're going to get. Yes, the red are the higher frequencies in this case, and the blue are the lower frequencies. Okay, so I'm just going to show a brief example of an EEG study that I found in the literature that uses this time frequency analysis. So they were looking at caffeine-consuming children and adolescents and how this alters their sleep behavior in deep sleep. So their deep sleep, we're going to be looking at slow wave activity, okay? And we're going to compare the effects of caffeine consumption on brain waves during sleep in these adolescents. So what they basically found was that they found later bedtimes in caffeine consumers, as well as reduced slow wave sleep and reduced alpha activity during sleep. Now, alpha activity are, again, those faster waves that you see when you're beginning to relax and try to fall asleep. Okay, so they looked at both the slow waves, which are shown across the row at the top, and they looked at the alpha waves, which are shown on the bottom. And so on the very left here are the caffeine consumers. In the middle colored plot are the controls. And then the plot next to that, the last color plot, are the difference between the caffeine consumers and the controls. And if you statistically analyze these differences, you can do t-tests, and you can come up with a t-value, which is what this black and white plot is on the right here. So you can see that there are definite differences between the caffeine consumers, adolescents, and the controls both in their slow wave and their alpha activity during sleep. Now, what this means as an implication as to physiologically, I'm not quite sure. I think if the paper probably goes into it a little bit, but it's a different sleep pattern from controls. Okay, so I mentioned that you can also do self-regulation with neurofeedback, and I've never really looked into this much before, but I saw when I was preparing this lecture that people were starting to do this. So it's kind of neat. So they hook someone up to an EEG, and they have this person actually watching their brain activity, and they're playing a video game essentially with their brainwaves. So we know that this is probably great in kids because we know that kids love to play video games these days. Well, my son does especially. So you're looking at this and you're trying to modulate your brainwaves to something more desirable. Now, I'm not quite sure what more desirable might be, but they probably have an idea before they tell this kid. And so you're trying to change frequencies at specific locations that are tailored to an individual. So they claim that this is a tool to self-regulate and improve your brain functioning. But I thought it was pretty interesting that you could look at your brain waves and try to change them just by adjusting maybe your level of relaxation or what you're thinking about. Okay, I also mentioned source localization, which is trying to find the main source of the EEG signal. So we know that the EEG signal is a summation of all the different places underneath the brain, underneath the skull, but where is the main part of the signal coming from? So where is the generator of these activities? So this is an inverse problem using the scalp measurements. So this is an inverse problem because we're looking at data that's coming from the scalp and trying to trace it to something inside the head rather than looking at something that goes from a starting point outwards. And this can be a very difficult problem because of the poor spatial resolution of the EEG. and it's not specifically a unique solution when you do these, because you can do all kinds of signal processing and end up with different places in the head. So it's a problem of singularity, and so it's a difficult technique. Back before we had functional MRIs and things that could spatially locate where different activity was coming from, this was a bigger problem, I believe, than it is today. So newer techniques have improved the methodology of source localization. And EEG and fMRI, like Mihir mentioned yesterday, at the same time would be a great thing to do, and people are certainly trying to work on making that happen. In clinical practice, the most common clinical use is localizing the source of seizures in epilepsy. Again, the patient is hooked up, scalp electrodes directly on the scalp or directly on the brain, and they wait for the seizure activity to occur. So when I was a graduate student, we had a little boy who had multiple seizures a day. I mean, he was seizing probably maybe every hour. It wasn't on the level of a grand mal seizure. A grand mal seizure is the one you think of when a person shakes and becomes unconscious, and you have to be very careful with them. You can have really small seizures that people can't notice, but it's still disrupting your activity on a daily basis. So they would hook this boy up, they opened his head up, and they would put him under video surveillance while he did different things and slept, to try to localize basically when his seizures were occurring based on all the data that they were collecting. And once they can find the location of the seizure, they often do surgery to either take that point out, or sometimes they'll cut total connections in the head. For example, they'll cut the corpus callosum so that the two parts of the brain don't talk to each other anymore, to try to isolate that seizure activity to a place in the brain. It's quite crude when you think of it, just cutting a chunk of the brain out, but it's still done today. And if the children are young enough, they usually have a full functional recovery after this surgery. So an epileptic seizure in EEG might look something like this. So the brain's going along normally, but a cell is firing, and the activity is so great that it's propagating through all the regions of the brain. Sometimes it's onset by some other kind of physiological issue. And epilepsy can also be fatal if you have a grand mal seizure and it's a bad outcome. So again, this is mostly done in children. They can put the electrodes directly on the skull, and again, they try to localize or find the origin of the seizures and do a focal cortical resection, which is cutting this area. And as I mentioned before, we do EEG and sleep staging. So different ways that you would assess sleep health using this would be to see how long a person stays in each stage of sleep, how many cycles of sleep a person goes through in a night. So the stages of sleep, again, are 1, 2, 3, 4, and REM, depending on what kind of EEG activity they see in these. So basically you cycle through stage 1, stage 2, you go into a deep sleep, and then you go back into REM sleep. And I believe one cycle of sleep is about 2 to 3 hours. So you go through several cycles a night. And when we go over sleep later, you'll see that sleep is quite an active process in the brain. It used to be believed that when you're sleeping, get up, you lazy bum, you shouldn't be sleeping all day. I'm looking at my mom. But now I can tell her sleep is a very active process that's necessary for the brain. MEG activity is similar to EEG. It was first measured in 1968. It measures the magnetic activity from the brain, not the electrical activity. You need to do this, you need very sensitive magnetometers. And they often have these giant machines called SQUIDs, superconducting quantum interference devices. And you put a person in these SQUIDs and you measure the activity. And I imagine they do similar things with the output that you would do with EEG. Okay, we're going to move on to PET. PET is positron emission tomography. That's the other functional technique we're going to talk about in some detail before we move on to MRIs. So again, we're going to go through what PET is, a brief history of it, how it works and the basic principles, how you would collect the data, and then we're going to talk about PET tracers, because when you measure PET data, you need to have a tracer or a molecule that you're trying to look at and see what happens to it when you put it into the body. We're going to talk a little bit about modeling and analyzing the data, problems of it, and applications of it. So PET scans are a nuclear medicine technique that measures body function. So you're using a radioactive tracer as a dye to measure some kind of function in the body. And you can measure blood flow with it, you can measure oxygen usage with it, you can measure glucose metabolism with it. So there's a lot of unique things that you can measure with PET that you can't measure with other types of imaging techniques. And if you see on the right there, this is sort of the early development stages of PET, the initial images, and as they got better throughout the 20 years shown here on the plot. So PET is a non-invasive, it's called non-invasive diagnostic imaging technique for measuring the metabolic activity of the cells. The only thing about PET is they call it non-invasive, but you use a radioactive tracer, so you do have to inject somebody with a radioactive dye. So when we want to study children or different things with PET, we have trouble doing that because of this injection of the radioactivity. It was developed in the mid-70s, and it was the first scanning method to give functional information about the brain. Other than EEG, we're talking like really localized to an image map. The tracer that's used is called a radionucleotide, and it's introduced into the body on a biologically active molecule. So we'll talk about this a little bit more when we talk about tracers. But basically, you mimic some kind of molecule in the body that the body uses naturally. You label it with this radio tracer. You put it into the body, and as the body metabolizes it or uses it, it releases this tracer. So you can see where this process and to the extent of which this process is taking place in the brain. It uses positrons, which I think are really cool because they are positively charged electrons, and this is also called antimatter. So antimatter, again, is the positively charged electrons, and we'll see how this works when we get a little bit more into the methods of it. So these positrons are emitted from your tracer, like I said, when the body uses it or takes it up as some kind of metabolic function way. When the positron is released, it immediately collides with an electron, and when it does this, it annihilates. So a positron collides with an electron and it annihilates. So that's why it's called antimatter, because the collision of the two gets rid of the matter. However, it does produce a pair of gamma rays that are emitted exactly 180 degrees apart. And I think this is a really clever technology because somebody thought of this and capitalized on this as a way to measure images in the brain. So again, the positron is an antimatter electron. It's an electron with a positive cell. It can come from different sources, but in PET specifically, they're produced by a nuclear decay process. And to make these positrons and to make them on tracers, a cyclotron is used. And it's used for the process of nuclear decay by bombarding a target material with protons. So it's actually a pretty complex method that's used to produce these tracers. As a result, a neutron is released and an unstable nuclei is produced, and this is the positron. Tracers can be used to measure, again, they can be used to measure glucose metabolism, oxygen. You can use them to measure dopamine receptors. And I worked at the PET Center at the University of Pittsburgh for about a year. And there they had developed this tracer they called Pittsburgh Compound B. And they use it to label and bind to amyloid plaques in Alzheimer's disease. So this was sort of a new discovery that came out of Pittsburgh. And we'll talk about it a little bit later, but it was something unique to the group that I worked with. And again, the picture on the left shows a basic schematic of what we're doing. So we're labeling this compound with our radionucleotide. We're injecting it into the body. When it binds or is used by the body, which is shown on the left there with the purple, so that's a picture of it binding to something, this radio tracer is released, and it comes from off of the molecule and goes up into the air, and then there is where it collides with the electron. So when it's released, it quickly collides with an electron. When the positive electron hits the negative electron, annihilation occurs, and the energy in the form of gamma rays is released exactly 180 degrees apart. And because of this, we can use a PET detector ring to register this event and determine where they came from. So we're going to show you a little picture here. They have these photon detectors around the person, and when they annihilate, again, they do 180 degrees apart, and you can actually detect a very, very sensitive down to the very milliseconds, or even maybe even finer, when these two pieces of gamma rays hit these protons. And you can use, again, this back propagation technique to trace where they're coming from and make us more specific, get a more specific idea of where in the brain this occurred. So the basic steps are: you inject a radio tracer into a subject. You have to wait until this radio tracer is absorbed, and some tracers take longer than others. You measure the tracer in the blood and brain at the same time, and then you perform a quantitative analysis to obtain biological data. So this quantitative analysis is not done in the case of every PET scan. Some things like glucose metabolism and studying things like cancer, you may not need to quantify this. You may just be able to look at the image and try to see where the spots where a lot of glucose metabolism is taking place. But when you do research studies, a lot of time you want to know specifically how much tracer is being used in relation to how much tracer you're injecting into the blood. So this sort of becomes a biochemistry problem at this point. So we're going to ask now, what is being used to create the image? What exactly are we making an image out of here? It's not light and it's not gamma rays, but it's these radioactive counts. So I guess it kind of is the gamma rays coming at the two locations of the detector at the same time. But the more counts in an area you get, the higher the image intensity. And these counts are called the standard uptake value, or the SUV. And if you're going to do a quantitative analysis, you're going to want to know what the concentration of this is in the region of the brain you're looking at, divided by how much tracer you initially injected into the body. So to do the image reconstruction, we're going to do this back propagation again. And it's the same idea that we used when we looked at CAT scanning. So the more projections you have, the better you can create an image. And you can see the 4 projections, 16 projections, and 128 projections, giving you a clear picture of the object on the top left. So the first tracer we're going to talk about, and the one we're going to talk about in most detail, is FDG. FDG is probably the most common PET tracer that is used. It is the only commercially available PET tracer, so you can actually purchase this from somewhere and use it. So it's used clinically. I think that's still true. I'm not 100% sure. But when I worked at the PET Center at the University of Pittsburgh, other tracers besides FDG had to be made specifically in the cyclotron at the PET Center. FDG is a glucose analog. So you can see the full name of it. It's 2-fluoro-2-deoxy-D-glucose. And it's, again, the most commonly used tracer. It has a half-life of 110 minutes. So you have to consider these half-lives in the timing of when you're going to take the PET image, because you don't want to wait too long and have most of the tracer already decayed before you try to measure the signal. So how does FDG work? So basically, FDG is a sugar molecule with F18 radioisotope attached to it. So it's mimicking the effect of glucose in the body. So we need glucose, which is basically a sugar, to convert energy in the body by the process of metabolism. So when your cells need energy, sugar is broken down into these molecules, into glucose, and we can use glucose as the energy as in the body. So if you substitute FDG for glucose and inject it into somebody, then you can measure where high levels of metabolism are occurring in the body. So we're looking at areas of the body that are eating up this glucose more quickly than others. And this is one reason why you can study cancer, because cancer occurs when cells are very rapidly dividing, and to do this they use a lot of energy. So if you sometimes PET scans are used to determine where there's active cancer in the body, and they do this by injecting and seeing which parts of the body are eating up this glucose the most quickly. And again, we're substituting this FDG and pretending that it's the glucose, but we can then trace the hot spots in the body and see where the metabolism is quickly occurring. So as you can see here, the glucose molecules on the left and our FDG molecules on the right. So it mimics the glucose molecule to an extent. Again, glucose is derived during metabolism through glycolysis, which is the breakdown of glucose into 2 ATP molecules and 2 NADH molecules. And I am certainly not a biochemist. I don't know if any of you are, but if you remember the Krebs cycle and the cycle by which glucose is converted into ATP, it starts at the beginning of cell respiration or cellular metabolism. Anaerobic metabolism is when the body is using oxygen to do this process, and anaerobic metabolism occurs when no oxygen is being used. So the body is pretty clever in knowing if it needs energy and you don't have enough oxygen to switch to this anaerobic metabolism. So FDG is taken up by the cells which use glucose as their primary energy source. Generally, you're going to try to do the scan 30 to 60 minutes post-injection. So again, the half-life is 110, so you don't want to wait too long. You want your tracer to be in the body and active when you're measuring your PET scan. So the body takes up FDG in a proportional way that it would take up glucose. And this FDG is broken down by the cell and leaves the body by passive diffusion. FDG and related compounds are cleared from non-cardiac tissues within 3 to 24 hours after administration. Clearance from the heart may require more than 36 hours, but essentially whatever's left in your body isn't just going to hang around there forever. The body's going to get rid of it. So after your PET scan is over, you don't have to worry about running around for the next couple years releasing these radioactive nucleotides. Are going to be cleared out of your body. And any FDGs that's not involved in the glucose metabolism is then excreted into the urine. Okay, so you can use FDG to study the brain in different ways. So on the left, we're looking at seizure activity, and we're looking at those different colors represent differences in how the glucose is being used in the brain. So you can see that seizure is causing this asymmetrical pattern of glucose use. And on the right is a brain that has on someone that has taken cocaine versus someone who's been given saline. So you can see the higher glucose metabolism is taking place in the saline brain. So the effects of the cocaine are changing the way that glucose is being taken up in the brain. There's a number of PET tracers other than FDG that are currently being used. A lot of these ones are research tracers. So a lot of these are newer, or you have people that sit around and think about these tracers a lot and try to make new ones and try to characterize different types of metabolisms or things that can be labeled in the body using these tracers. Okay, so we're going to talk a little bit about PET modeling. And when I did a quick search on PET modeling on the internet, this is the first thing that popped up. So apparently people do other types of PET modeling as well. So when you do PET modeling, you want to quantify the amount of tracer that's detected in the tissue. So, and because once you have this information, you can get it how it's being metabolized or used in the body. So you want to try to quantify this information. And to model this, the reason that we would want to do this for different people is because there's different patient sizes, and this introduces variability. And because different people might use a tracer to a different extent than another would be. So standard tracers like FDG are well characterized, so you don't need to collect the blood as the PET scan is being done. But other newer tracers, like the Pittsburgh Compound B, require blood flow modeling. And one thing about this Pittsburgh Compound B tracer was that when it was in the newer stages, they actually needed to collect arterial blood from these people as they were getting their PET scans. So if you know anything about collecting blood, you know that it's much harder to get arterial blood than it is venous blood. The venous blood is the blood that is coming back to the heart after it's gone through the body, whereas the arterial blood is still being sent out to the tissue, so it's full of this tracer and full of the oxygen still that's going to go to the tissue. And to get arterial blood, you usually have to make a cut. So these people that were in these research studies, and you want to get a deep blood vessel, so they had to be taken down into the surgery department where they would set this arterial line up before these people had these PET studies. To do this, you do this kinetic modeling that you see sometimes in biochem, where you do these compartments and you model the blood and the brain, that the part of that's not metabolized and the part of the brain that is metabolized. And PET people are very good at generating these models and understanding them. But just to get an idea, do you remember these K factors was how these K factors represent how quickly things are being metabolized and flowing into one compartment versus another. So in this type of model here, we would assume that once the tissue, the tracer goes from the blood to the brain, it's not metabolized, and then once it's metabolized, it can't unmetabolize. So in this case, our K4 constant would be set equal to 0, and you need to model K1, K2, and K3. And again, you would do this by collecting the blood, taking measurements and seeing how much tracer is in the blood, and then trying to measure what's being used in the brain with the PET scans. A semi-quantitative analysis would be where the images are summed and normalized to the patient weight and dose, and this would give you the standard uptake value, which is what we're trying to measure, how much tracer is being released from this person. And if you're going to do a fully quantitative model, then's when you need to start using these compartment models. You can do a 2-tissue model or a 3-tissue compartment model. And to simplify this type of modeling, people have come up with other methods to do so. They have come up with graphical analyses, and there's a technique called Patlack modeling that uses this, and they've also come up with more simplified kinetic models. So Patlack modeling is a quantitative method, so you use graphical techniques based on the compartment model, and you use a linear regression technique to identify and analyze the pharmacokinetics of the tracer. So the way that this tracer is being used and metabolized and going back and forth from the blood to the brain is called pharmacokinetics. So you're measuring the kinetics, basically, of the pharmaceutical element that you're using. The quantitative PATLAC model like this is model independent, and the behavior of the tracer is approximated by 2 compartments in this model. So if you guys want to learn more about this, I'm sure you can find all kinds of things in the literature. At one point, I had a good understanding of this, but it's been a while. But I know it's pretty complicated. So here's the equation for it. And again, by using this type of model, you can plot the points, and so you take this equation on the top and you make it into a linear equation. So you can see the second equation underneath there could be used as a linear equation where x equals y equals mx plus b. And by doing that, you get a model of, you can model the slope of the line and where it crosses the intercept graphically. And to do that, then by doing that, you can estimate the parameters of k and v0. You can get time activity curves by what the concentration is doing over time with these measurements. So you can see in this plot, the concentration of the tracer in the blood is dropping quickly, while in the body it's rising, and in the brain, the non-metabolized is first taken up pretty quickly and then drops. And what's being metabolized is increasing slowly and then sort of leveling out over time. Okay, that's my brief thing on PET modeling. And I'm going to talk really quickly about problems of PET imaging. The first thing is that it uses ionizing radiation. So like I said initially, the PET people also often call it non-invasive, but it's injecting somebody with radiation. So sometimes people have problems with this. It often requires a very long scan time. It depends on the tracer and the half-life of your tracer. So one problem that we have is that people sometimes can't lie still for that long, especially if some certain clinical populations. And what they used to do at the PET center is they would take a piece of plastic, a soft plastic, and they would mold it to the person's face. And then they would put this on top of the person's face while they were getting the PET scan to try to hold them in place so they couldn't move while they were collecting this data. PET scans are pretty low resolution compared to MRIs and CAT scans. So that means these little chunks of data that we're getting are bigger than they would be with MRIs or CAT scans. And the tracers can be pretty expensive. So they have to be made on site in these cyclotrons. And these cyclotrons are, again, creating the antimatter. So they're quite an impressive piece of equipment, I think. Should we stop for today and finish this tomorrow? Do you guys have other things to do? I know it's noon now. Let me see how many more slides are here. I have probably about 10 more here. So we can, if you want, we can go over some of the clinical uses of PET tomorrow before we start talking about MRI. Oh, yeah, that's true. Well, I'll leave it up to you guys. Stay or go. Tomorrow? And you guys want to complete it? All right, let's complete it. Okay. So you can use the FDG and PET again to study areas of high glucose uptake. So you might have areas of high glucose uptake in malignant cancer cells, and also brain cells use a lot of energy, muscle cells or renal cells. So you can see here, this is an FDG scan. I think the next one will show up more. But you can see here the heart is lining up. It looks like the bladder is lining up here. So you can actually see the high energy use areas in the body. You can use it to study metabolic diseases or study glucose-related diseases like diabetes. So this would be somebody who has lung cancer here. And you can see these hot spots lighting up here in the body. This is, whoops. This is somebody who has a pelvic tumor. So you can see again, there's areas of the body that are already use high levels of glucose, the brain and the heart. But this area here again shows an unusual amount of glucose metabolism, indicating that there's active cancer activity going on there. Here's an example of thyroid cancer. You can also take these images and make them into color based on what intensity levels you're seeing and get a prettier picture from those. This is a picture of glucose metabolism, different types of PET tracers in the same person. Okay, so this person had a head injury, and you can see on the CAT scan here where the injury occurred, right over here. And this is a cerebral blood flow scan. So this is using oxygen metabolism. And you can see how, okay, so this is another type of oxygen scan with a different tracer. This is blood flow. And this is oxygen usage. And this is also another type of oxygen usage. And this is a glucose image. So you can see how different tracers might give you different information about the same type of thing. And I think I have time to read all that, but it has to do with how the body is responding to this injury in the head. Something interesting that they used to do at the University of Pittsburgh was look at this tracer called a raclopride, and that was used to mark the dopamine usage in the head. So this is a healthy volunteer on the top, and on the bottom here is somebody with Parkinson's disease. And so you can see there's differences, especially in this image. This is the raclopride image of how this dopamine is looking in the brain, and it looks to me like there's less dopamine, which is part of what your diagnosis in Parkinson's is a lack of this dopamine levels. Okay, I briefly mentioned this Pittsburgh compound B, and they use this to study Alzheimer's disease. These amyloid plaques that are created during Alzheimer's disease can be labeled with this compound B, and imaging studies using this can help indicate a diagnosis of Alzheimer's. So typically in the past, and a lot really kind of today still, Alzheimer's disease can only be confirmed as a confirmed diagnosis post-mortem by looking at the brain and seeing that there were these plaques and tangles that occurred. So there were two guys that I worked with at the University of Pittsburgh that were the first that created and used this Pittsburgh compound B. And what it does is it binds to the plaques and tangles, and you can mark them, and then when you do the image, you can see that there's amyloid plaques developing in the brain. So this is the pathology, what it looks like. So here's a normal brain, and in Alzheimer's, these neurons start getting what they call tangles, and they appear in the image as just being tangled up in a sort of a disorganized mess. And you also get these plaque deposits in the brain. So if you mark it with Pittsburgh compound B, then you can actually start to image these plaques in the brain. This is a control, and this is MCI, means mild cognitive impairment. So you can see that they had 3 different patients that had mild cognitive impairments and a person with Alzheimer's disease. And the red areas are where you can see these amyloid plaques building up. So this person with cognitive impairment didn't seem to have any plaques, whereas this person here may actually have not only this mild cognitive impairment, but may also have Alzheimer's disease. An interesting thing, so this is looking at, this is more of the amyloid deposits. So an interesting thing about this Pittsburgh compound B and these amyloid plaques is that they were imaging control subjects and imaging these Alzheimer's subjects to see the differences in these amyloid deposits. And a strange thing that they saw was in some of these control subjects, they saw that these people had amyloid plaques already in their brain. So which is kind of scary if you come in to do a control study and you see that you have plaques in your brain already. So because this technique was so early, they weren't sure at the time whether these people were going to go on to develop Alzheimer's disease, or if people just had some people just had these plaques in their brain at a baseline level. So it got kind of scary, and no one wanted to get in the scanner and be a control because no one wanted to know if they had plaques in their brains or not. Okay, so we'll talk about fMRI tomorrow and some other techniques as we go on. But in summary, I just wanted to say that the EEG and PET imaging, I showed this slide earlier, but with these advancements in these techniques, it just causes the amount of brain research going on in the past 10 years to really skyrocket. So that's all I have for today. Thank you for staying extra. And thank you again for your attention. And I will see everyone tomorrow. If you have any questions, please let me know.